I've been sort of lax about looking at people's reading response questions, and I looked at 3.5, which is the section on the generalized uncertainty principle. And almost everyone was asking questions on the energy-time uncertainty relationship, but some of you asked questions on the derivation of it, which I didn't do in class. And I'm happy to talk to you about it outside of class, but again, I just didn't think it made the cut of being sufficiently interesting. So if you want to know about some technical step, how Griffiths is getting from here to there, here's one asking about how to think about it, or what's the use of it. So Griffiths makes this big deal about energy is conserved in quantum mechanics. We talked about the meaning of that. It doesn't mean exactly the same thing as it does in classical mechanics. But he makes in no uncertain terms that we shouldn't think of that delta E times delta T is greater than or equal to h bar over 2 as meaning that you can borrow energy. But then the question is, what exactly is it implying? And the takeaway message I want you to have is that when a state, states in quantum mechanics are generically a superposition of energy eigenvalues, right? There's no such, very seldom would you be in a definite energy state. If you're randomly choosing a state, most of them are superpositions of different energies. But if you're very close to a definite energy state, then that uncertainty relation tells you that the system is going to change very slowly. In other words, the amount of time it takes any dynamical variable to change by 1 standard deviation is going to be very long. If the uncertainty in energy is very small, that means you're in almost a definite energy state. I sort of de-emphasize that maybe compared to Griffiths, but it is something that you talk about in modern physics, so maybe that's why there's so much discussion on it. Okay, so and I made a mistake on Friday. I probably should have had you read 3.6 for today, but that's okay. We're just going to let it wash over us. It's on. I put it on for Wednesday, so sometime in the next couple of days, read 3.6. 3.6 is sort of developing the Dirac notation kind of stuff. And we did a worksheet at the end of Friday talking about Dirac notation. But you're going to see a lot of things work out really nicely in this notation, but it's unfamiliar to us. And so that means that we've got to practice with using it. We're used to working in different notation. When we're talking about matrix multiplication, it's going to look a little bit weird in Dirac notation, but you'll see there's a lot of advantages. I've already emphasized that, what we mean by this Dirac notation, we're going to come to call this a ket in the bra-ket notation. I don't know if you talk about that term in modern physics, but we're going to denote it just like, we would in introductory physics as a V with a little arrow over the top. So that means if I'm thinking of a specific vector, there's only one of those, and we're using this to denote it. No matter which way we're going to tell you about the vector, right? In good old physics 210, you might say, well, I could give you the xy components, or I could give you the angle and the length of the vector, and both of those would tell us something about what vector we're talking about. So we need a name that's independent of those. Nonetheless, we can choose a lot of different bases, and we didn't do this so much in introductory physics, but in quantum mechanics, we're beginning to figure out that these different bases are like our different representations. The position representation is one way of giving the information about a vector. Energy representation and momentum representation are the other two big ways of giving it. So we've got to know about going between them, and you already know something about changing bases. If I have a vector, it's going to have different components in the x1, x2 basis, or xy basis, than it will in the w1, w2 basis. And the way I find components, maybe you're not used to thinking of it this way. So here I'm saying this vector v has a projection vx1 onto vector x1 hat. That's a unit vector. That's a basis vector in the x1, x2 basis. And this is what we would call its component, of course, right? And so this is expanding it in terms of components and basis vectors. So this is like saying 3x hat plus 2y hat. Notice that to get that component, you take the inner product of the vector that we're talking about with the unit vector. Right? The component is nothing but the inner product of the vector with the unit vector. That's like saying if you want to get Vx, you take V dot x hat, and that would give you what Vx is. Maybe you're not used to thinking of it that way. Another thing that's going to be maybe unusual is that here I've written it in summation notation. So this means the same thing here. There are only two things in the sum, so it's not a very exciting sum, but we're saying here are the components and here are the unit vectors. So this is nothing but an expansion in a particular basis, and these things right here are the components. If I switch bases, I get a very similar kind of expression, right? In terms of the W1, W2 unit basis vectors, the orthonormal set of basis vectors, this is what the expansion would look like. And these things down here are the components in those. The components are going to be different. Okay. Now, in quantum mechanics, similarly, there's only going to be one state that we're talking about, right? A particle, whatever state it's in at a particular time, there's one state. But there's many ways to represent that state. In other words, we can write it as a linear combination of any complete orthonormal set of vectors. We can use states of definite energy as our basis vectors, states of definite position as our basis vectors. We'd call that the position representation, and states of definite momentum. So those are the big three. Let's go through what those look like. So we already talked about, it's a little bit strange, but we have a set of basis vectors which are the state of definite position. Right? So when I say that vector, let's just write something on the board here. When I say the state x equals 3 meters or something, just to be very definite. That's supposed to be a part of, that's representing the state of a particle that is definitely going to be measured at 3 meters and not anywhere else on the x-axis, right? So that would mean if we were talking about the probability density as a function of x, and here is 3 meters right there, it should be 0, 0, 0. Well, there should be an area 1 under the curve. So it's going to have to be some kind of Dirac delta function there. And we talked about how it seemed like when we wrote down the eigenvalue equation, the states of definite position were Dirac delta functions, right? So I've got one state for here, one for here, one for here, one for here. There's an infinite continuous collection of these states. They're a little bit strange that way. Okay, so we can expand. If we have a state, we might call it, at a particular time, or, our state is generically a function of time. So again, we had a worksheet last week where we emphasized the fact that whatever goes inside this angle, bracket, and line here is just a label. And you can use that label however you want, although there are some more usual ways of doing it. So I might say, I'm going to call my state psi. And of course, psi depends on time. The state that the particle is in, the way, at least in the position representation, we would say how the wave unfolds with time is going to change. So at one time, it's in a different state than it is at a different time. Let's just call that psi of t. In order to expand it in this basis, we have a continuous collection of these basis vectors, right? One for each x value. What we do is take the inner product of that state with each of those, and those are our components, and then we have to add them up for all of those different vectors, but adding when you have a continuous collection is just integration. So here we're integrating over, these are the coefficients, and these are the basis vectors, and we're adding them all up in a linear combination, right? So those things underneath the squiggly brace are the components. And usually this inner product of psi at each time with the state of definite position is what we call psi of x and t. So this is our usual good old fashioned time dependent wave function that we were talking about back in chapter 2 that's appearing right here. Okay, it's sort of an unfamiliar context, maybe, or unfamiliar notation. Similarly, the same state, psi of t, could be expanded in the states of definite momentum. Right? We already found out the states of definite momentum are proportional to e to the I kx. Well, we have to put in k equals p over h bar. So our states of definite momentum, at least as functions of x, look like this: a times e to the I kx, but k is equal to p over h bar. P equals h bar k. So that's writing it as a function of momentum. And these will be Dirac orthonormalized. We're reassured. We didn't prove this. If we put a 1 over root 2 pi h bar out in front, then that we, we would normally call this maybe, what did I call these back then? I might call this fp of x. And then with that normalization, it's going to be true that the inner product between fp prime of x and fp of x with that normalization is exactly delta of p minus p prime. No other constants out in front. Okay, so they're Dirac orthonormal, just like these position basis vectors are Dirac orthonormal. We can expand it in a similar way, right? I could say psi of t, that state, is a linear combination of these definite momentum vectors, and these are the components. The state at time t, inner product with the state of definite momentum, is what we usually call phi of p and t, and that's what we call our momentum space wave function, right? So trying to pull all this stuff together. And then finally, this one's sort of familiar to us from chapter 2. We used this a lot back then. If we take our complete orthonormal set of basis vectors to be the collection of energy operator eigenvalues, and of course eigenvectors, and of course we need to know what potential we're talking about, but maybe we're talking about the harmonic oscillator potential, and so there's some states of definite energy in that case, and we'll label them like this: either En, I can't remember, maybe this is Griffith's notation, just n. Sometimes I label it either way, right? But these are the nth definite energy state, right? And here I'm using the labeling as if they're the harmonic oscillator ones, starting n from 0. But in other problems, it might start at 1. I can write that psi as a linear combination of those states of definite energy, and the coefficients, these are the things that we called Cn before, the inner product of psi with the state, the nth definite energy state. Okay, so that's writing this in terms of Dirac notation. So we're seeing that a single vector has different components with respect to different orthonormal bases. It's also true, and we mentioned this before, that an operator will have different matrix elements. Linear operators, the way we're used to thinking of them as matrices, but they're going to have different matrix elements with respect to different representations: position, momentum, and energy. Okay, so let's see how to find those matrix elements, and part of what we're going to do today is get practice calculating matrix elements of operators. So again, this Q hat is supposed to be an abstract description of the operator. Just like V, there's only one V I'm talking about. There's only one operator, Q hat, maybe P hat or X hat or H hat. There's only one operator, but there are lots of different ways to represent it. And so we're going to define what the matrix elements are. I've lost control of my clicker again here. Okay. So let's imagine, just to get to familiar ground again, let's imagine we're in 3 dimensions, right? I've got basis vectors, E1, E2, E3. Those could be like our X hat, Y hat, Z hat in 3-dimensional space, right? Let's just write them as a collection of basis vectors. Then we're going to define the matrix elements of the operator in this particular basis to be QMN, where QMN is defined as Q acting on EN, and then take the inner product with EM hat. Okay. And one thing you got to remember back from your whenever you first learned about matrices, whether it's in linear algebra or just a physics context, whenever you have a matrix, the first index that we do always means the row index of the matrix, and the second one is column. Everything with matrices is always row, then column. So if you can remember that, that's easy, or makes it easier. So let's practice with some of this just to remind ourselves of, uh-oh, I didn't bring these worksheets, but luckily my office is just down the hall. So let me go grab them. For those of you on Zoom, I believe that this is the third worksheet that was posted under Friday's date. So take a look at that. It should say matrix notation at the top of the worksheet. So we're just doing problem 1 on this worksheet, and it's to force you to remind yourself about matrices. Because we're going to be calculating a lot of matrix elements and manipulating them in this section. Okay, I just sent out a second email because I realized I forgot to post another worksheet that we were going to use today on the website. So if you're on Zoom, once we start doing the next worksheet, that should be in your inbox now. Okay, let's look at this worksheet. It's just to force you to remember about matrices and how we denote them. So we've got matrix elements A11, A12, A13, A21, and so on. And when we're talking about those matrix elements, how do we conventionally put them into an array or into a matrix that we display like this, right? Well, A11 goes up there. What's the argument that A12 goes there and not down there? Right, I mean, I'm just forcing you to think, oh, row 1, yes, I'm in row 1, column 2, that's where I am, right? So A13, A21, A22, and so on, okay? That's how we put those 9 elements in there. That was A. Questions on that? Because we're, you know, we're gonna enter more, less familiar context where we have an infinite number of these, or maybe we have a continuum here and we've really got to be familiar with keeping those straight. B says, suppose a vector alpha is a vector in a 3D vector space, which has components alpha 1, alpha 2, alpha 3 in the orthonormal basis of part A. Okay, so there's some orthonormal basis up there. Then, where am I here? And suppose that A alpha equals beta. I better write this down. A operating on alpha transforms it into the basis, the vector beta. Then write out that has components beta 1, beta 2, beta 3 in this orthonormal basis. Write out longhand how to compute beta 2 in terms of the various aij and alpha I. So this is really trying to decode this. We're saying, let me write this somewhere else up here. I want to write down in matrix notation, A acting on alpha is equal to beta. Here's my representation in particular basis of A. We're told in the same basis, this vector has components alpha 1, alpha 2, alpha 3. So I can write it as a column vector. And to compute the components of the result, you know, this would be beta 1, beta 2, beta 3. And so what I'm asking you to write out is, how do you compute that number beta 2 or that component beta 2? Well, hopefully, I don't know how people remember this, but to me, I say, oh, to get beta 2, I multiply the second row times the first column, right? Because we're looking for something in the second row there, and there's only one column to choose from there, right? So second row times first column. When I say row times column, I mean first one times first one plus second one times second one plus third one times third one, right? So this would, the formula would be A21 alpha 1 plus A22 alpha 2 plus A23 alpha 3. That's how you get beta 2. Okay? C says rewrite it in summation notation. Well, I can write a sum here over the second index, right? So I could say beta 2 is equal to A2J alpha J summed from J equals 1 to 3. Isn't that what we're doing? We're going to see a lot of expressions like this, but maybe you're not used to writing it in summation notation. Okay, now that we got it for beta 2, it's pretty easy to write how do you get the ith component of beta? Well, this is how you get beta 2. To get beta I, we just put an I there. So we're going to see this kind of thing appearing a lot. When you see this, it's supposed to remind you of matrix multiplication. Now, it doesn't necessarily look visually like this, but this is what we mean by matrix multiplication. So some formula like that. Questions on that? All right, good. We'll come back to the second problem on that a little bit later. Share screen. Okay. Now, let's see how, I mean, right now, this is just a definition, but let's see how this definition makes sense in terms of this operation here. So I'm imagining I'm going to write down various ways of describing that when Q operates on alpha, it turns it into beta. Okay, that's how we write it in abstract vector notation. If we wanted to write it in a particular basis, we could say, well, I skipped a step here, I see. We could say, well, let's just write out what's true in this basis we were talking about in this problem. The sum from j equals, well, the sum from j equals 1 to 3 of beta I EI is equal to Q acting on the sum from, why is this a sum over J? Or a sum over I, right? Sum I equals 1 to 3 of alpha I EI. Something like that. And then what can I do with the Q? Well, this is a linear operator. In fact, every operator we're going to talk about in quantum mechanics is linear. And what does linear mean? It means when it encounters a linear combination of vectors, it can distribute over the addition and it can move through the constants. So this Q I can put right next to that vector. That's the next line that I kind of skipped over there. Right? So I have just written out beta in terms of components and alpha in terms of components in a particular basis. So that's a same statement, but in a particular basis. Now, what I'm going to do with each of these sides, these two sides are equal. Let's take the inner product with EM. Okay, this is a vector. I can take its inner product with EM. That means the EM is going to appear on the left-hand side of the inner product. So I'm going to put an EM over here with the left-facing angle thing. And again, you have to look back to your definitions or the properties of an inner product. When you have an inner product of a sum of a bunch of things with constants, you can distribute the inner product over the sum and pull the constants out in front. In this case, without any star on them when they're appearing just in front of the ones on the right-hand side. So I've taken the inner product with EM here, and I've also taken the inner product with EM here and distributed that inner product over the sum and the various constants. So here's what's left after I move the EM through all the stuff that isn't a vector at all. It's just a sum and a bunch of scalars. Now, why was I doing that? Well, I wanted to interpret the matrix elements here. So these are the matrix elements of this operator Q. This is the Mn matrix element of Q. And EM, inner product with En, we're assuming this is an orthonormal basis that we're doing this in. We're always going to use orthonormal or Dirac orthonormal bases. Here I'm assuming it's a discrete basis. We're back in 3D vector space, right? So EM, inner product En is delta Mn, right? X hat dot Y hat is 0, but X hat dot X hat is 1. That's saying the same thing. And therefore, when I simplify, right, use this delta Mn in this summation, we would say, well, we've got an infinite number of terms, but every one of them is 0 except where n equals m. So that's going to turn this left-hand side into just a beta m, right? And on the right-hand side, I can just rewrite it in terms of the matrix elements. And we're seeing here exactly what we just encountered. This is telling us that in this basis, the equivalent statement to Q hat on the vector alpha gives the vector beta is you do matrix multiplication on the components and you get that vector. Okay, so we're sort of justifying the definition of this being the matrix elements. That's how we calculate matrix elements. Okay, so now let's start doing it in quantum mechanics context and say, we've sort of gotten a little bit of intuition on the notation from 3D vector spaces. So let's imagine that, just to start out in the easier cases, let's imagine we have an orthonormal basis that's discrete. Now, so we're not talking about Dirac orthonormal, but we're talking about a basis where there's going to be an infinite number of basis vectors, but we don't have to think of a continuum of them. Okay, so let's imagine we have a Hermitian operator. It represents an observable. And let's imagine we know the spectrum of that operator, the collection of eigenvalues of that operator, and the spectrum is discrete. Okay, then anytime I have a Hermitian operator with a discrete spectrum, I can form a basis, an infinite basis of eigenvectors of that. And we talked about how to make it orthonormal. Mostly it comes out naturally orthonormal unless we have degeneracy, and then we have to work a little bit to force it to be orthonormal. Okay, so we're imagining that's going to be our basis. The basis is going to be the eigenvectors of Q hat, and let's find the matrix elements of a different operator, A. A may not be Hermitian, but if we want to find the matrix elements of A in the QM basis, to do that, by definition, these are the matrix elements, except there are an infinite number of them, right? Maybe I didn't specify. Yeah, here I'm saying let's take n going from 1 to infinity. So n goes from 1 to infinity, m goes from 1 to infinity. And this is really an integral, right? We're saying do an inner product, but sandwich this operator A between it, right? So if I want to do this the good old-fashioned inner product way, I sandwich it between Qm as a function of x, so whatever this state is, Fqm as a function of x and Fqn as a function of x. This one needs a star on it. I sandwich it between it and do an integral. So each one of those numbers is an integral to be done. And sometimes we can do all those integrals in just one fell swoop. Sometimes we have to think about each one, and each one is extremely painful, right? And we've got an infinite number of them. Maybe we can get the first few of them, depending on things, okay? So, and again, the same sort of thing follows as we talked about before in 3 dimensions. If A turns vector alpha into beta, the equivalent statement in terms of matrix elements is when we do matrix multiplication of the matrix elements of alpha of A, that vector operator, on the components thought of as a column vector here, we get the components as a column vector of the vector beta. That's a particular basis kind of interpretation of this abstract statement. Okay, now we're going to think about a particularly simple case. We were talking about 2 operators there, right? One was a Hermitian operator Q, and we said every time you have a Hermitian operator Q with a discrete spectrum, it has an orthonormal collection of basis vectors, right? Complete orthonormal set of basis vectors, and we were talking about those in the previous one. But we were also talking about some vector A. What if that vector A is the operator Q, sorry, not vector, but operator. What if that operator A is the operator Q itself, for which these are the eigenvectors of that operator? Well, things simplify enormously. And this worksheet is not the next one on that, but it's on a different worksheet. So if you're on Zoom, I forgot to post it on the website, so this is in your inbox now. It is a worksheet with matrix elements at the top. And we're just going to do 1A right now. We'll talk about 1B in a minute, but 1A, you can see from the space I left there, is easy. There's not much work to be done here. So here we're imagining we're in the context of the infinite well potential with the usual between 0 and A. And we want to find the matrix elements of the Hamiltonian corresponding to that potential in the energy basis or the energy representation, however you want to say it there. So in symbols, we might write that as, you know, EM H hat EN, right? That's what the symbol HMN is going to be defined as. So calculate HMN, and you should find that you don't have to do an infinite number of separate integrals. It's really easy. Something just happens so that you really don't have to do any integrals. Okay, so you're either knowing which way to go, maybe you're done. But which way do I go from here? What's the next step? Yeah, I know by definition, this is an eigenvector of this operator. And the reason we chose this notation is because it's telling me what the corresponding eigenvalue is, right? It's saying it's an eigenvector with eigenvalue En, where En is n squared pi squared h bar squared over 2ma squared, that a good old formula, right? So this is equal to, just to put it out in longhand, Em. I'm going to put En here just as a shorthand, En. Then what do I do? Sorry, I couldn't hear. Yes, well, so what do I do with this one that's sitting in the middle? That would be, you know, sometimes it helps if you're just confused about this notation to go back to what the integral definition would be. You know, this would be like, I have an integral of, you know, something like a psi m star of x. And let's suppose that En is the number 2, right? And then I've got a psi n of x dx. What can I do with this number? I can pull it out in front. In fact, it's not going to be imaginary because this is a Hermitian operator we're talking about. But even if it were an imaginary number, I could pull it out in front of the thing. That's right. So the eigenvector is always between an angle and a line like that, right? And so when something's outside of there, it might be a number. A number is a kind of operator, a very degenerate one, but it could be an operator there, and we're thinking of it as being sandwiched between those two things. When we write it as an integral, this is the one that gets the star. This is the one that doesn't get the star. This is something that's sandwiched between. But yeah, one of our properties is that we can factor that En out in front, and then we're left with Em and En. And I think Mackay told me that this is what? Yeah, Kronecker delta. This is delta Mn. So this is 0 unless n is equal to n, and therefore I can just write this as Em. Okay, so this is just to sum up. We're saying, sorry, I shouldn't write it that way. This is saying that Mn is equal to En times delta Mn. Now let's think about how to write that out as a matrix, right? I want to write it as an array because that's what mostly we're familiar with. Let's write out the matrix elements of HMN. Well, the first thing to realize is that Unless the row index is equal to the column index, we're talking about zeros, right? So we've got some diagonal elements here which might not be zero, but everything else out here is a bunch of zeros, you know? Sometimes people just, you know, just to denote that, they'll put big zeros there. They'll say this is a diagonal matrix. There's all zeros, super diagonal and sub-diagonal, right? And then what goes in the 1, 1 location? Well, I just plug in m equals 1 and n equals 1. This gives a value 1, and this gives E1, right? So I get E1 there. Similarly, I get E2 and E3, and so on down the diagonal. So there really wasn't much of a computation to do there. And what this is saying is that every Hermitian operator, in this case, we were just doing the specific case of the Hamiltonian, but you know, the generic case is displayed on the slide. So let's go back to those now. So if we go forward, here's what happened, right? This was our Hamiltonian, this was our state of definite energy. Now we've got some Hermitian operator, and this is a state of definite Q in the discrete spectrum case. So Q operating on this state denoted by Qn. The whole reason we chose that notation is because we get a Qn out in front of there. And then in the same way, we can pull that Qn out in front of the inner product, and this thing is delta Mn. And so this is a diagonal matrix, right? Same way here, we get whatever the smallest value is here. And I should say, you know, if we were talking about an eigen a spectrum where we started at n equals 0, we would just start labeling the row and column at 0 instead of 1. They don't always have to start at 1 in this case, but the first one goes up here and so on. So what it's saying is that any Hermitian operator, its matrix elements computed in its own eigenbasis is a diagonal matrix. So in its own eigenbasis, it's as simple as a matrix can get, or that's one of the simplest kinds. I guess a slightly simpler matrix would either be the 0 matrix or where the same number was all down the diagonal, but this is pretty simple on the scale of matrices. Okay, and that's what that says there. Okay, let's take the case where we're not in its own eigenbasis. So now this is the case we talked about earlier where, again, I'm going to take these to be eigenvectors of some Hermitian operator, and they've been orthonormalized, and they form a discrete collection of vectors. But now they aren't eigenvectors of this operator. This operator is not related to it in any special way. Okay, this is what the matrix elements are. And again, we got to do one integral for each m and n value. And what I want you to do is, in that worksheet we were just looking at, that you did 1A with the Hamiltonian there, now try 1B. And you know, it might get a little bit messy. You need to use the integral that's given there in 1B, but at least start it and see if you can get the idea. And then I will show you what the numerical values are in the matrix together. So here we're talking about the operator we want the matrix elements for is the momentum operator, and we want the energy basis. Again, we're in the context of the infinite square well. So just to do the first step together to make sure we're on the same page here, right? If we need to compute this and it's not that diagonal case we just did, we actually have to write this out as an inner product. And to do the inner product, you can't do it abstractly. You have to do it in a particular representation. We know what these definite energy states are in the position representation. In other words, as functions of x. EM is root 2 over a times the sine of m pi x over a. I don't need a star on there because it's a perfectly real function, but normally we do put a star on this one in the inner product. And then we're told to sandwich the momentum operator between, so that's minus I h bar d dx. And then I've got a root 2 over a times the sine of n pi x over a. And we've got to integrate. That's what our inner product means. So see if you can see how to use the integral that's given there. Okay, so I gotta try to use that integral formula, which unfortunately is a multi-part formula, so it makes a bit of a mess, but let me try to combine these together. All I did was take the derivative, I pulled out all the constants, take the derivative of the sine, you get a cosine times an n pi over a from the chain rule of the cosine, and so up to the constants, that's the integral I have to do, and that's exactly of the form that we're given. So this is equal to minus I h bar times 2n pi over a squared, not my favorite collection of constants, times, and we're told that this has two cases. The case where if m is equal to n, then that's the case a is equal to b. So maybe we'll write that down first, right? If m is equal to n, maybe I'll do some work over here. If m equals n, then the antiderivative that we're left with is minus cosine squared of ax, a we'll call the first one, m pi x over a. That's cosine of ax plus a constant, right? And then we've got to evaluate that. It doesn't matter what the constant is, because when we evaluate this between, oh, and I see I made a mistake here, right? Already here. This is only the function between minus 0 and a, right? Same thing here. So it's 0 everywhere else between minus infinity to infinity. So I already should have specialized up here from 0 to a. Got ahead of myself, right? So I've got to evaluate, if m equals n, I need to evaluate between 0 and a. So when I do the lower limit, I get an extra minus sign from that. That cancels out that one. And when I plug in here, cosine of 0 is 1. So that will give a 1. And then the upper limit will have the minus sign with it. Cosine squared of m pi. Okay, does that agree with what I have here? Oh, I forgot the 1 over 2a in my integral formula. I put in the cosine squared ax, but we need divided by 2 times a, and a is this stuff. 2 times m pi x over a. Well, it's getting to be kind of a mess, but in any case, I need to evaluate that between 0 and a, and the claim is, in addition to this stuff here, I get a 1 over 2 m pi over a. Okay, that's the case where m is equal to n. That would be the diagonal elements we're finding out there, right? You tell me which diagonal point I'm on, compute this number. That tells me what the value is in that diagonal one, okay? The other one's kind of messier. I'll write it down and not worry about computing it. 1 minus the cosine of m minus n times pi over 2 m minus n pi over a, m minus n pi over a, plus some other ugly term, 1 minus the cosine of m plus n times pi, kind of the analogous term with minus replaced with plus, over 2 m plus n pi over a. Okay, and that's the case m not equal to n. And then I've got to plug in different m's and n's and figure out what those numbers are, right? You give me an m and an n, it tells me what row and column I am in the matrix, and I can compute the number from this. Now that's not, when I look at that formula, I don't get a lot of insight, but let's put it in MATLAB and see what comes out. And here's what it is. The mn components of the momentum operator in the energy basis in this case, I guess I'm claiming that these are all 0. See, all my diagonal elements are 0. When m equals n, cosine of m pi is either plus or minus 1, but we're squaring it, so that gives 1, and we're subtracting by 1, so the numerator is 0. So all the diagonal elements are 0, we're finding out there. That's what we're seeing along the diagonal. And the other ones, I just put those formulae into MATLAB and had it spit out the numbers there, and there they are, with you know, the constants out in front that we've been carrying along. You know, given that I didn't explain the whole thing, the process that we're going through is the important thing. So any more questions on that? All right. Okay, now let's take the more difficult case. What about if Q What about if our basis vectors don't form a discrete set, but rather a continuous set? Well, looking at the time, I'm seeing we're not going to get through this. It's 1:39 according to that clock right there, which I assume it's been corrected now. Yeah. So you can imagine what's going to happen. This is a continuum. This is a continuum here. The simplest case is just like this one, where these are the corresponding Dirac orthonormalized eigenvectors of this operator. That's the simple case. That's like the diagonal case. And we'll do this at the beginning of Wednesday, but we're going to let this operate on this state. If it's an eigenvector, we'll get the eigenvalue out in front. We'll pull that out in front, and we'll have a Q prime and a Q there and get a delta function out of it, because we're assuming they're Dirac orthonormalized with respect to that parameter Q. Okay, so, but I see it's 1:40 now, so that's a good break point to stop at, and we'll keep working on the continuous matrix elements next time. And we'll talk about continuous matrix multiplication. How do you take a continuous matrix times a continuous column vector and do matrix multiplication? We're really doing the same thing, but we're integrating instead of summing. All right. So hang on to that homework. Do the last few of the homework. Oh wait, were they due today or they due Wednesday? I can't remember. The last ones in there, the last ones that are covered on the exam are due today. 5 through 8, and I think, yes, okay. So the ones that are due on the day of the test are also ones that are relevant. They have to do, the ones for today had to do with eigenvalue equations, finding eigenvectors and eigenvalues. The ones for Wednesday have to do with generalized uncertainty principle and stuff like that. So take a look at those, and you can turn in both those assignments together at the exam on Thursday. All right. See you on Wednesday, if not before.